Chapter 1. Matter in our surroundings. As we look at our surroundings, we see a large variety of things with different shapes, sizes, and textures. Everything in this universe is made up of material which scientists have named matter. The air we breathe, the food we eat, stones, clouds, stars, plants, and animals, even a small drop of water or a particle of sand, everything is matter. We can also see as we look around that all the things mentioned above occupy space and have mass. In other words, they have both mass asterisk and volume asterisk asterisk. Since early times, human beings have been trying to understand the surroundings. Early Indian philosophers classified matter in the form of 5 basic elements: the Panchtapa, air, earth, fire, sky, and water. According to them, everything, living or non-living, was made up of these 5 basic elements. Ancient Greek philosophers had arrived at a similar classification of matter. Modern-day scientists have evolved 2 types of classification of matter based on the physical properties and chemical nature. In this chapter, we shall learn about matter based on its physical properties. Chemical aspects of matter will be taken up in subsequent chapters. 1.1 Physical nature of matter. 1.1.1 Matter is made up of particles. For a long time, 2 schools of thought prevailed regarding the nature of matter. One school believed matter to be continuous like a block of wood, whereas the other thought that matter was made up of particles like sand. Let us perform an activity to decide about the nature of matter. Is it continuous or particulate? Activity 1.1. Take a 100 milliliters beaker. Fill half the beaker with water and mark the level of water. Dissolve some salt sugar with the help of a glass rod. Observe any change in water level. What do you think has happened to the salt? Where does it disappear? Does the level of water change? In order to answer these questions, we need to use the idea that matter is made up of particles. What was there in the spoon, salt or sugar, has now spread throughout water. This is illustrated in figure 1.1. Figure 1.1, when we dissolve salt in water, the particles of salt get into the spaces between particles of water. 1.1.2, how small are these particles of matter? Activity 1.2. Take 2 to 3 crystals of potassium permanganate and dissolve them in 100 milliliters of water. Asterisk the SI unit of mass is kilogram, kilogram. Asterisk asterisk the SI unit of volume is cubic meter, M3. The common unit of measuring volume is liter, L, such that 1 L equals 1 cubic decimeter, 1 L equals 1000 milliliters, 1 milliliter equals 1 cc. Take out approximately 10 milliliters of this solution and put it into 90 milliliters of clear water. Take out 10 milliliters of this solution and put it into another 90 milliliters of clear water. Keep diluting the solution like this 5 to 8 times. Is the water still colored? Figure 1.2, estimating how small are the particles of matter. With every dilution, though the color becomes light, it is still visible. This experiment shows that just a few crystals of potassium permanganate can color a large volume of water, about 1000 L. So we conclude that there must be millions of tiny particles in just one crystal of potassium permanganate, which keep on dividing themselves into smaller and smaller particles. The same activity can be done using 2 milliliters of detal instead of potassium permanganate. The smell can be detected even on repeated dilution. The particles of matter are very small, they're small beyond our imagination. 1.2 Characteristics of particles of matter. 1.2.1 Particles of matter have space between them. In activities 1.1 and 1.2 we saw the particles of sugar, salt, detal, or potassium permanganate got evenly distributed in water. Similarly, when we make tea, coffee, or lemonade, nimbu pani, particles of one type of matter get into the spaces between particles of the other. This shows that there is enough space between particles of matter. 1.2.2 Particles of matter are continuously moving. Activity 1.3. Put an unlit incense stick in a corner of your class. How close do you have to go near it so as to get its smell? Now light the incense stick. What happens? Do you get the smell sitting at a distance? Record your observations. Activity 1.4. Take 2 glasses beakers filled with water. Put a drop of blue or red ink slowly and carefully along the sides of the first beaker and honey in the same way in the second beaker. Leave them undisturbed in your house or in a corner of the class. Record your observations. What do you observe immediately after adding the ink drop? What do you observe immediately after adding a drop of honey? How many hours or days does it take for the color of ink to spread evenly throughout the water? Activity 1.5. Drop a crystal of copper sulfate or potassium permanganate into a glass of hot water and another containing cold water. Do not stir the solution. Allow the crystals to settle at the bottom. What do you observe just above the solid crystal in the glass? What happens as time passes? What does this suggest about the particles of solid and liquid? Does the rate of mixing change with temperature? Why and how? From the above 3 activities 1.3, 1.4, and 1.5 we can conclude the following. Particles of matter are continuously moving, that is, they possess what we call the kinetic energy. As the temperature rises, particles move faster. So, we can say that with increase in temperature, the kinetic energy of the particles also increases. In the above 3 activities, we observe the particles of matter intermix on their own with each other. They do so by getting into the spaces between the particles. This intermixing of particles of 2 different types of matter on their own is called diffusion. We also observe that on heating, diffusion becomes faster. Why does this happen? 1.2.3 Particles of matter attract each other. Activity 1.6. Play this game in the field, make 4 groups and form human chains as suggested. The first group should hold each other from the back and lock arms like IDU Mishmi dances, figure 1.3. Figure 1.3. The second group should hold hands to form a human chain. The third group should form a chain by touching each other with only their fingertips. Now, the fourth group of students should run around and try to break the 3 human chains one by one into as many small groups as possible. Which group was the easiest to break? Why? If we consider each student as a particle of matter, then in which group the particles held each other with the maximum force? Activity 1.7. Take an iron nail, a piece of chalk, and a rubber band. Try breaking them by hammering, cutting, or stretching. In which of the above 3 substances do you think the particles are held together with greater force? Activity 1.8. Take some water in a container, try cutting the surface of water with your fingers. Were you able to cut the surface of water? What could be the reason behind the surface of water remaining together? The above 3 activities 1.6, 1.7, and 1.8 suggest that particles of matter have force acting between them. This force keeps the particles together. The strength of this force of attraction varies from one kind of matter to another. Questions. 1. Which of the following are matter? Chair, air, love, smell, hate, almonds, thought, cold, lemon water, smell of perfume. 2. Give reasons for the following observation. The smell of hot sizzling food reaches you several meters away, but to get the smell from cold food you have to go close. 3. A diver is able to cut through water in a swimming pool. Which property of matter does this observation show? 4. What are the characteristics of the particles of matter? 1.3 States of matter. Observe different types of matter around you. What are its different states? We can see that matter around us exists in 3 different states: solid, liquid, and gas. These states of matter arise due to the variation in the characteristics of the particles of matter. Now, let us study about the properties of these 3 states of matter in detail. 1.3.1 The solid state. Activity 1.9. Collect the following articles: a pen, a book, a needle, and a piece of wooden stick. Sketch the shape of the above articles in your notebook by moving a pencil around them. Do all these have a definite shape, distinct boundaries, and a fixed volume? What happens if they are hammered, pulled, or dropped? Are these capable of diffusing into each other? Try compressing them by applying force. Are you able to compress them? All the above are examples of solids. We can observe that all these have a definite shape, distinct boundaries, and fixed volumes, that is, have negligible compressibility. Solids have a tendency to maintain their shape when subjected to outside force. Solids may break under force, but it is difficult to change their shape, so they are rigid. Consider the following. What about a rubber band? Can it change its shape on stretching? Is it a solid? B. What about sugar and salt? When kept in different jars, these take the shape of the jar. Are they solid? C. What about a sponge? It is a solid, yet we are able to compress it. Why? All the above are solids. A rubber band changes shape under force and regains the same shape when the force is removed. If excessive force is applied, it breaks. The shape of each individual sugar or salt crystal remains fixed whether we take it in our hand, put it in a plate, or in a jar. A sponge has minute holes in which air is trapped. When we press it, the air is expelled out and we are able to compress it. 1.3.2 The liquid state. Activity 1.10. Collect the following. Water, cooking oil, milk, juice, a cold drink. B. Containers of different shapes. Put a 50 milliliters mark on these containers using a measuring cylinder from the laboratory. What will happen if these liquids are spilt on the floor? Measure 50 milliliters of any one liquid and transfer it into different containers one by one. Does the volume remain the same? Does the shape of the liquid remain the same? When you pour the liquid from one container into another, does it flow easily? We observe that liquids have no fixed shape but have a fixed volume. They take up the shape of the container in which they are kept. Liquids flow and change shape, so they are not rigid but can be called fluid. Refer to activities 1.4 and 1.5 where we saw that solids and liquids can diffuse into liquids. The gases from the atmosphere diffuse and dissolve in water. These gases, especially oxygen and carbon dioxide, are essential for the survival of aquatic animals and plants. All living creatures need to breathe for survival. The aquatic animals can breathe underwater due to the presence of dissolved oxygen in water. Thus, we may conclude that solids, liquids, and gases can diffuse into liquids. The rate of diffusion of liquids is higher than that of solids. This is due to the fact that in the liquid state, particles move freely and have greater space between each other as compared to particles in a solid state. 1.3.3 The gaseous state. Have you ever observed a balloon seller filling a large number of balloons from a single cylinder of gas? Inquire from him how many balloons is he able to fill from one cylinder. Ask him which gas does he have in the cylinder. Activity 1.11. Take 3 100 milliliter syringes and close their nozzles by rubber corks, as shown in Fig. 1.4. Remove the pistons from all the syringes. Leaving one syringe untouched, fill water in the second and pieces of chalk in the third. Insert the pistons back into the syringes. You may apply some Vaseline on the pistons before inserting them into the syringes for the smooth movement. Now, try to compress the content by pushing the piston in each syringe. Figure 1.4. What do you observe? In which case was the piston easily pushed in? What do you infer from your observations? We have observed that gases are highly compressible as compared to solids and liquids. The liquefied petroleum gas (LPG) cylinder that we get in our home for cooking or the oxygen supplied to hospitals in cylinders is compressed gas. Compressed natural gas (CNG) is used as fuel these days in vehicles. Due to its high compressibility, large volumes of a gas can be compressed into a small cylinder and transported easily. We come to know of what is being cooked in the kitchen without even entering there by the smell that reaches our nostrils. How does this smell reach us? The particles of the aroma of food mixed with the particles of air spread from the kitchen reach us and even farther away. The smell of hot cooked food reaches us in seconds. Compare this with the rate of diffusion of solids and liquids. Due to high speed of particles and large space between them, gases show the property of diffusing very fast into other gases. In the gaseous state, the particles move about randomly at high speed. Due to this random movement, the particles hit each other and also the walls of the container. The pressure exerted by the gas is because of this force exerted by gas particles per unit area on the walls of the container. Fig. 1.5 A, B, and C show the magnified schematic pictures of the three states of matter. The motion of the particles can be seen and compared in the three states of matter. Questions. 1. The mass per unit volume of a substance is called density. Density equals mass volume. Arrange the following in order of increasing density: air, exhaust from chimneys, honey, water, chalk, cotton, and iron. 2. Tabulate the differences in the characterized set of states of matter. B. Comment upon the following: rigidity, compressibility, fluidity, filling a gas container, shape, kinetic energy, and density. 3. Give reasons. A. A gas fills completely the vessel in which it is kept. B. A gas exerts pressure on the walls of the container. C. A wooden table should be called a solid. D. We can easily move our hand in air, but to do the same through a solid block of wood we need a karate expert. 4. Liquids generally have lower density as compared to solids. But you must have observed that ice floats on water. Find out why. 1.4 Can matter change its state? We all know from our observation that water can exist in three states of matter. Solid as ice, liquid as the familiar water, and gas as water vapor. What happens inside the matter during this change of state? What happens to the particles of matter during the change of states? How does this change of state take place? We need answers to these questions, isn't it? 1.4.1 Effect of change of temperature. Activity 1.12. Take about 150 grams of ice in a beaker and suspend a laboratory thermometer so that its bulb is in contact with the ice, as in figure 1.6. Start heating the beaker on a low flame. A. B. Note the temperature when the ice starts melting. Note the temperature when all the ice has converted into water. Record your observations for this conversion of solid to liquid state. Now, put a glass rod in the beaker and heat while stirring till the water starts boiling. Keep a careful eye on the thermometer reading till most of the water has vaporized. Record your observations for the conversion of water in the liquid state to the gaseous state. On increasing the temperature of solids, the kinetic energy of the particles increases. Due to the increase in kinetic energy, the particles start vibrating with greater speed. The energy supplied by heat overcomes the forces of attraction between the particles. The particles leave the fixed positions and start moving more freely. A stage is reached when the solid melts and is converted to a liquid. The minimum temperature at which a solid melts to become a liquid at the atmospheric pressure is called its melting point. The melting point of a solid is an indication of the strength of the force of attraction between its particles. The melting point of ice is 273.15 K asterisk. The process of melting, that is change of solid state into liquid state, is also known as fusion. When a solid melts, its temperature remains the same, so where does the heat energy go? You must have observed during the experiment of melting that the temperature of the system does not change after the melting point is reached till all the ice melts. This happens even though we continue to heat the beaker, that is, we continue to supply heat. This heat gets used up in changing the state by overcoming the forces of attraction between the particles. As this heat energy is absorbed by ice without showing any rise in temperature, it is considered that it gets hidden into the contents of the beaker and is known as the latent heat. The word latent means hidden. The amount of heat energy that is required to change 1 kilogram of a solid into liquid at atmospheric pressure at its melting point is known as the latent heat of fusion. So, particles in water at OOC 273 K have more energy as compared to particles in ice at the same temperature. When we supply heat energy to water, particles start moving even faster. At a certain temperature, a point is reached when the particles have enough energy to break free from the forces of attraction of each other. At this temperature, the liquid starts changing into gas. The temperature at which a liquid starts boiling at the atmospheric pressure is known as its boiling point. Boiling is a bulk phenomenon. Particles from the bulk of the liquid gain enough energy to change into the vapor state. For water, this temperature is 373 K. 100 C equals 273 plus 100 equals 373 K. Can you define the latent heat of vaporization? Do it in the same way as we have defined the latent heat of fusion. Particles in steam, that is water vapor at 373 K, 1000 C, have more energy than water at the same temperature. This is because particles in steam have absorbed extra energy in the form of latent heat of vaporization. So, we infer that the state of matter can be changed into another state by changing the temperature. We have learned that substances around us change state from solid to liquid and from liquid to gas on application of heat. But there is some that change directly from solid state to gaseous state and vice versa without changing into the liquid state. Asterisk note: Kelvin is the SI unit of temperature. OOC equals 273.15 K. For convenience, we take OOC equals 273 K after rounding off the decimal. To change a temperature on the Kelvin scale to the Celsius scale, you have to subtract 273 from the given temperature, and to convert a temperature on the Celsius scale to the Kelvin scale, you have to add 273 to the given temperature. Activity 1.13. Take some camphor or ammonium chloride. Crush it and put it in a china dish. Put an inverted funnel over the china dish. Put a cotton plug on the stem of the funnel, as shown in figure 1.7. Now, heat slowly and observe. What do you infer from the above activity? Figure 1.7. Sublimation of ammonium chloride. A change of state directly from solid to gas without changing into liquid state is called sublimation, and the direct change of gas to solid without changing into liquid is called deposition. 1.4.2 Effect of change of pressure. We have already learned that the difference in various states of matter is due to the difference in the distances between the constituent particles. What will happen when we start putting pressure and compress a gas enclosed in a cylinder? Will the particles come closer? Do you think that increasing or decreasing the pressure can change the state of matter? Figure 1.8. By applying pressure, particles of matter can be brought close together. Applying pressure and reducing temperature can liquefy gases. Have you heard of solid carbon dioxide, CO2? It is stored under high pressure. Solid CO2 gets converted directly to gaseous state on decrease of pressure to 1 atmosphere asterisk without coming into liquid state. This is the reason that solid carbon dioxide is also known as dry ice. Thus, we can say that pressure and temperature determine the state of a substance, whether it will be solid, liquid, or gas. Figure 1.9. Interconversion of the three states of matter. Questions. Asterisk atmosphere, ATM, is a unit of measuring pressure exerted by a gas. The unit of pressure is Pascal per 1 atmosphere equals 1.01 times 105 pascals. The pressure of air in atmosphere is called atmospheric pressure. The atmospheric pressure at sea level is 1 atmosphere and is taken as the normal atmospheric pressure. 1. Convert the following temperature to Celsius scale. A. 300 K. B. 573 K. 2. What is the physical state of water at A. 250 C. B. 100 C. 3. For any substance, why does the temperature remain constant during the change of state? 4. Suggest a method to liquefy atmospheric gases. 1.5 Evaporation. Do we always need to heat or change pressure for changing the state of matter? Can you quote some examples from everyday life where change of state from liquid to vapor takes place without the liquid reaching the boiling point? Water, when left uncovered, slowly changes into vapor. Wet clothes dry up. What happens to water in the above two examples? We know that particles of matter are always moving and are never at rest. At a given temperature in any gas, liquid or solid, there are particles with different amounts of kinetic energy. In the case of liquids, a small fraction of particles at the surface having higher kinetic energy is able to break away from the forces of attraction of other particles and gets converted into vapor. This phenomenon of change of a liquid into vapors at any temperature below its boiling point is called evaporation. 1.5.1 Factors affecting evaporation. Let us understand this with an activity. Activity 1.14. Take 5 milliliters of water in a test tube and keep it near a window or under a fan. Take 5 milliliters of water in an open china dish and keep it near a window or under a fan. Take 5 milliliters of water in an open china dish and keep it inside a cupboard or on a shelf in your class. Record the room temperature. Record the time or days taken for the evaporation process in the above cases. Repeat the above 3 steps of activity on a rainy day and record your observations. What do you infer about the effect of temperature, surface area, and wind velocity, speed on evaporation? You must have observed that the rate of evaporation increases with an increase of surface area. We know that evaporation is a surface phenomenon. If the surface area is increased, the rate of evaporation increases. For example, while putting clothes for drying up, we spread them out. An increase of temperature. With the increase of temperature, more number of particles get enough kinetic energy to go into the vapor state. A decrease in humidity. Humidity is the amount of water vapor present in air. The air around us cannot hold more than a definite amount of water vapor at a given temperature. If the amount of water in air is already high, the rate of evaporation decreases. An increase in wind speed. It is a common observation that clothes dry faster on a windy day. With the increase in wind speed, the particles of water vapor move away with the wind, decreasing the amount of water vapor in the surrounding. 1.5.2 How does evaporation cause cooling? In an open vessel, the liquid keeps on evaporating. The particles of liquid absorb energy from the surroundings to regain the energy lost during evaporation. This absorption of energy from the surroundings makes the surroundings cold. What happens when you pour some acetone, nail polish remover, on your palm? The particles gain energy from your palm or surroundings and evaporate, causing the palm to feel cool. After a hot sunny day, people sprinkle water on the roof or open ground because the large latent heat of vaporization of water helps to cool the hot surface. Can you cite some more examples from daily life where we can feel the effect of cooling due to evaporation? Why should we wear cotton clothes in summer? During summer, we perspire more because of the mechanism of our body which keeps us cool. We know that during evaporation, the particles at the surface of the liquid gain energy from the surroundings or body surface and change into vapor. The heat energy equal to the latent heat of vaporization is absorbed from the body, leaving the body cool. Cotton, being a good absorber of water, helps in absorbing the sweat and exposing it to the atmosphere for easy evaporation. Why do we see water droplets on the outer surface of a glass containing ice cold water? Let us take some ice cold water in a tumbler. Soon we will see water droplets on the outer surface of the tumbler. The water vapor present in air, on coming in contact with the cold glass of water, loses energy and gets converted to liquid state, which we see as water droplets. Questions. 1. Why does a desert cooler cool better on a hot dry day? 2. How does the water kept in an earthen pot maca become cool during summer? 3. Why does our palm feel cold when we put some acetone or petrol or perfume on it? 4. Why are we able to sip hot tea or milk faster from a saucer rather than a cup? 5. What type of clothes should we wear in summer? Now scientists are talking of 5 states of matter: solid, liquid, gas, plasma, and Bose-Einstein condensate. Plasma, the state consists of superenergetic and superexcited particles. These particles are in the form of ionized gases. The fluorescent tube and neon sign bulbs consist of plasma. Inside a neon sign bulb there is neon gas, and inside a fluorescent tube there is helium gas or some other gas. The gas gets ionized, that is, gets charged when electrical energy flows through it. This charging up creates a plasma glowing inside the tube or bulb. The plasma glows with a special color depending on the nature of gas. The sun and the stars glow because of the presence of plasma in them. The plasma is created in stars because of very high temperature. SN. Bose. 1894-1974. Albert Einstein. 1879-1955. Bose-Einstein condensate. In 1920, Indian physicist Satyendranath Bose had done some calculations for a fifth state of matter. Building on his calculations, Albert Einstein predicted a new state of matter, the Bose-Einstein condensate Beck. In 2001, Eric A. Cornell, Wolfgang Kettle, and Carl E. Women of USA received the Nobel Prize in Physics for achieving Bose-Einstein condensation. The Beck is formed by cooling a gas of extremely low density, about 100,000th the density of normal air, to super low temperatures. You can log on to get more information on these fourth and fifth states of matter. What you have learned. Matter is made up of small particles. The matter around us exists in 3 states: solid, liquid, and gas. The forces of attraction between the particles are maximum in solids, intermediate in liquids, and minimum in gases. The spaces in between the constituent particles and kinetic energy of the particles are minimum in the case of solids, intermediate in liquids, and maximum in gases. The arrangement of particles is most ordered in the case of solids. In the case of liquids, layers of particles can slip and slide over each other, while for gases, there is no order. Particles just move about randomly. The states of matter are interconvertible. The state of matter can be changed by changing temperature or pressure. Sublimation is the change of solid state directly to gaseous state without going through liquid state. Deposition is the change of gaseous state directly to solid state without going through liquid state. Boiling is a bulk phenomenon. Particles from the bulk whole of the liquid change into vapor state. Evaporation is a surface phenomenon. Particles from the surface gain enough energy to overcome the forces of attraction present in the liquid and change into the vapor state. The rate of evaporation depends upon the surface area exposed to the atmosphere, the temperature, the humidity, and the wind speed. Evaporation causes cooling. Latent heat of vaporization is the heat energy required to change 1 kilogram of a liquid to gas at atmospheric pressure at its boiling point. Latent heat of fusion is the amount of heat energy required to change 1 kilogram of solid into liquid at its melting point. Some measurable quantities and the units to remember. Exercises. 1. Convert the following temperatures to the Celsius scale. At 293 K, B, 470 K. 2. Convert the following temperatures to the Kelvin scale. At 25 degrees Celsius, B, 373 degrees Celsius. 3. Give reason for the following observations. At naphthalene balls disappear with time without leaving any solid. B. We can get the smell of perfume sitting several meters away. 4. Arrange the following substances in increasing order of forces of attraction between the particles: water, sugar, oxygen. 5. What is the physical state of water at 25 degrees Celsius, B, 0 degrees Celsius, C, 100 degrees Celsius. 6. Give 2 reasons to justify. The water at room temperature is a liquid. B. An iron almirah is a solid at room temperature. 7. Why is ice at 273 K more effective in cooling than water at the same temperature? 8. What produces more severe burns, boiling water or steam? 9. Name A, B, C, D, E, and F in the following diagram showing change in its state. Group activity. Prepare a model to demonstrate movement of particles in solids, liquids, and gases. For making this model, you will need a transparent jar, a big rubber balloon or piece of stretchable rubber sheet, a string, few chickpeas or black gram or dry green peas. How to make. Put the seeds in the jar. Sew the string to the center of the rubber sheet and put some tape to keep it tied securely. Stretch and tie the rubber sheet on the mouth of the jar. Your model is ready. Now run your fingers up and down the string by first tugging at it slowly and then rapidly. Figure 1.10, a model for converting of solid to liquid and liquid to gas.